Last lecture, we left the story of galaxy development around 1 to 2 billion years after the Big Bang, equivalent to 5 to 10-year-old children. At that time, the galaxies were small and chaotic, a few thousand light years across. Galaxy collisions and mergers were common. Star birth rates and supernova explosions were at an all-time high. It was a wild and spectacular time. In this lecture, I want to pick up where we left off and follow the story forward 11 or 12 billion years to today. How did those little blobby dwarf galaxies mature into the large, majestic, modern-day galaxies, the beautiful spiral and ellipticals that we see all around us today? The story is actually not unlike that for humans, in the sense that each of our lives has its own specific trajectory that takes us from child to adult. But there are also common events that most of us experience, like school or marriage or a career. And it's like that for galaxies. Each has its own specific history, but there are common processes that many galaxies experience. So it's these common processes I want to look at in this lecture. And our very first process is a fabulous one. It's galaxy-galaxy collisions. You should have been expecting this, because a fundamental part of the overall story is hierarchical assembly. Small things merge to make larger things, which merge to make yet larger things. So let's look in more detail at what happens when galaxies collide. Well, just like a car accident, there is a range of possible collision damage, depending on whether the impact is a glancing blow, or head-on, or on whether the collision involves two cars or two trucks, or a car and a truck. And sometimes, like on a foggy interstate, there can be a multi-car, multi-galaxy pile-up. Now, the story of how we've come to understand what happens when galaxies collide spans 20 years and is a lovely example of a close collaboration between observations and computer simulations. So in this lecture, I'll be jumping back and forth between real images of galaxies and computer simulations. Now, the computational story got underway in the early 1970s when two brothers, Alaa and Yuri Toomre, calculated what happens to the stars orbiting one galaxy when a smaller galaxy passes by some distance away. Here's the output from their relatively simple computations. The sequence unfolds with 50 million years between each step. As the small galaxy passes the larger one, its gravity affects the orbits of the stars, and they no longer travel on nice, neat circles, but move out in larger arcs. And when you look at the whole collection, the pattern makes two huge, pretty spiral arms that astronomers call tidal arms, because their formation is similar to the way the moon's gravity raises tides on the Earth's oceans. Here are a few examples of real galaxies experiencing flybys. You can see very well this primary feature: two arms, one towards and one away from the companion. It's a clear sign of gravitational tidal interaction. Now, since those early days of limited computing speed and memory, things have improved enormously. Today's simulations routinely include 100 million stars all pulling on each other according to Newton's laws of gravity and motion. Actually, those 100 million computational objects are shared amongst the various galaxy components. Not only the disk and bulge stars, but also the dark matter particles that make up the heavy halo. See, don't forget that a dark matter particle follows a trajectory just like a star would, because it doesn't collide with anything. So it's very fortunate that the enormously important role of the dark matter can be included in the simulation as just another component. Let's start gently with a fascinating process called galactic cannibalism, when a big galaxy slowly shreds and devours a smaller one. Here's a simulation of a small galaxy in orbit about a big one. The big galaxy's gravity gradually shreds the small one. The shredded stars enter similar, but not identical, orbits that both lead and trail the small galaxy in what are called tidal streams. After a few orbits, the streams extend right around the big galaxy, and in time, the small galaxy may be shredded away to nothing. In effect, it's been eaten, and its stars have now joined the halo of the big galaxy. Actually, what prompted these particular computer models was the discovery of half a dozen or so tidal streams around our own Milky Way galaxy. So it seems we inhabit a galaxy with cannibalistic tendencies, although it's now thought that this steady ingestion of small galaxies by big ones is a routine part of a big galaxy's life. Here, for example, are two galaxies with prominent tidal streams in orbit about them. Well, having looked at small galaxies interacting with large ones, let's now up the drama and look at a full-blown, head-on collision between two large spiral galaxies. So in this simulation, the disk stars are coloured blue, the bulge stars are coloured yellow, and the dark matter is coloured red. The whole movie lasts just 15 seconds, but that covers 1.5 billion years. So time is passing at a rate of 100 million years per second. That's from the dinosaurs to now in just 1 second of movie time. So off we go. As they approach, there is some spiral structure induced in each disk. Then at closest passage, there is wholesale destruction of both disks, and fabulous tidal arms are flung out. Now, I've paused the movie here to compare with a famous pair of interacting galaxies called the Mice. The agreement is remarkably good, though, of course, the initial setup conditions for this particular simulation were chosen to match this particular pair of interacting galaxies. I hope you noticed how both galaxies effectively passed through each other, like two flocks of birds might fly right through each other. No stars ever collide. Now, this makes sense when you remember our scale model from Lecture 2. If the United States is a galaxy, then stars are tiny human cells separated by football fields. So when these galaxies collide, you can see that no cells, no stars, will hit each other. All the effects that you see are caused by gravity gently modifying each star's trajectory. Okay, let's continue the simulation. Notice how the relatively dense galaxy centers turn around and merge very quickly. You can really feel the strength of the central gravitational field. On the other hand, the outer parts evolve quite slowly, as those tidal features gradually wrap around and make basically quite a mess. The final state shows a single galaxy, one center, one bulge, and one halo. The two disks have been destroyed, and although some of the original disk stars have joined the final bulge, others make up a complex set of faint tidal features outside the main galaxy. So now let's look at some examples of real galaxies that resemble various stages of that calculation from early to late. Of course, each is a different pair, but you can see in these examples many of the features that you saw in the movie. This last one certainly has all the hallmarks of a late-stage merger, complete with a complex set of outer tidal debris. Now, if you run these computer simulations longer, those outer halo features gradually get more and more washed out, like these galaxies here. And ultimately, the system resembles a nice, smooth, elliptical galaxy, like this one. This is a fascinating result. It seems that a galaxy's type, spiral or elliptical, can change as time goes by. At least some ellipticals once used to be spirals until they got into a bad accident. So galaxies don't necessarily just change incrementally. Occasionally, they undergo a sudden, total transformation. Now, there's more to the story of galaxy collisions because we've not yet considered what happens to the thin gas that exists between the stars, the interstellar gas. Now, this is very important because stars are born from this gas, so we want to know what happens to it during the collisions. Now, let's begin with the computer simulations. Now, gas behaves in a much more complicated way than either stars or dark matter, and it wasn't until the 1990s that computers were sufficiently powerful to include it in the calculations. Now, this sequence helps us see what happens. The left side shows the stars and dark matter. Actually, their motion is pretty much unaffected by the gas, and you can see the merger unfold from one panel to the next. However, unlike the stars, the gas from each galaxy doesn't simply pass through, but instead it collides at high speed, and the force of the collision both compresses and heats the gas. Now, what happens next is rather complex, but the upshot is that some of the gas remains hot and expands outwards. That hot gas is shown in the middle sequence, where the blue, green, and purple show the temperature from 20,000 degrees to 2 million degrees. However, some of the gas is able to cool, and it quickly gathers to the center of the galaxy. That's shown in the right sequence, where black, blue, and red show gas of higher and higher density. Now, I said before that gas can give birth to stars. So, in all this chaos during the collision, are any stars born? And the answer is an emphatic yes. And it's not hard to see why. The compression resulting from the colliding gas clouds is enough to trigger the gravitational collapse to form stars. Also, the gas that goes to the center is now in a high-pressure environment that's quite conducive to forming stars. So the upshot is that when galaxies collide, stars are born in huge numbers. Galaxy collisions are extremely fertile events. Now, observationally, the link between galaxy interactions and collisions and high starbirth rates is very obvious indeed. For reasons I don't have time for, a classic symptom of high starbirth rate is the emission of lots of far infrared radiation. Now, the first satellite telescope sensitive to this type of radiation was launched in the 1980s, and almost immediately it became apparent that galaxies that shone brightly in the far infrared, like these four here, were also in the throes of an interaction or a merger. These galaxies had huge amounts of gas in their nuclei and were birthing stars at a rate of 100 or even 1,000 stars per year. That is much higher than the normal 1 or 0.1 new stars per year for a normal galaxy like the Milky Way. Galaxies with this kind of elevated star formation are called starburst galaxies, because the episode of elevated starbirth is usually quite short-lived. After about 100 million years, all the gas is used up or is blown out of the galaxy, so starbirth shuts down. Perhaps the most famous example of a starburst is the pair of colliding galaxies called the antennae. And when the Hubble telescope zooms into the central regions, the image is shot through with the signatures of very high rates of star birth. Now that we've begun to understand how gas behaves during galaxy collisions, we can also begin to understand the star birth history of the whole universe. Now, we met this topic last lecture with the Madaw plot. It showed the initial baby boom of high star formation, which is thought to be due to the high frequency of galaxy collisions in the young universe. But could the later drop in star birth rate be due to a drop in the collision rate? Absolutely. Using the Hubble telescope's deep surveys, you can measure the fraction of galaxies that are colliding right across cosmic history. In the young universe, almost all galaxies were colliding, while in the current universe, only about 2% are colliding. This isn't surprising. As time passes, galaxies are getting further apart due to cosmic expansion. And in addition, they're combining, and so there are fewer remaining to collide. So it's pretty clear that at least part of the reason for the drop in cosmic star birth rate is due to the gradual decline in the number of galaxy collisions. Let's now shift gears and look at how the primary parts of a modern-day galaxy gain their identity. The huge dark matter halo, a roughly spheroidal bulge of stars, and a relatively flat rotating disk made from both stars and gas. How were these components assembled? Well, in a sense, we've already looked at how the halos and bulges form. They're thought to be assembled during the initial collapse and ongoing collisions and mergers. If we use our merger tree from last lecture, the halos and bulges are growing at these intersections during mergers. But what about galaxy disks? Disks are thought to grow during the relatively quiet times between mergers. They involve a more gentle acquisition of gas that falls in from the surroundings. Here's a movie that shows the growth of a gas disk across several billion years. The movie shows only the gas, even though stars and dark matter are also in the calculation. Compared to the other movies, there's a different feel to this one. The collapsing objects rotate, and when they merge, the gas settles even more, although some is also heated and blown out. Even when modest collisions disturb the disk, it still seems to recover and continues to grow by pulling in gas. Finally, when the disk is relatively isolated with no more mergers, it settles down, rotates, and even forms spiral arms. Remember from lecture 18 that the crucial difference between gas and either stars or dark matter is that gas is collisional and dissipative, meaning that it can't interpenetrate like stars or dark matter. It collides and compresses, and the energy of the collision can be radiated away as photons. It can be dissipated. And because of this, the gas settles down towards the center of the halo and forms a rotating, thin disk. Now, although I've just described the formation of a rotating disk of gas, don't forget that over time, gas forms stars, which themselves inherit the orderly circular rotation of the gas. So over time, then, the disk builds up a population of stars. That's the current situation with our own Milky Way galaxy. We've not had a major merger for several billion years, and during that time, both gas and stars have gradually built up to make a significant disk. In fact, 4.5 billion years ago, some of that gas condensed to form the Sun and planets, and here we are. The Sun has an approximately circular orbit within the disk of the Milky Way galaxy. Actually, unmolested disks, left to themselves, have a gentle evolution of their own. As the hundreds of millions of stars orbit, they gently pull on each other, and although it's difficult to intuit what happens in this collective assembly, patterns form, spiral arms, rings, and bars. These may last a long time, or they may be transient, but they give their galaxies some of the most beautiful appearances in nature. Now, part of my story about disk construction was their need for relative isolation. Disks are fragile things and can be disturbed or destroyed relatively easily. Now, observationally, this is very obvious when you look at where spiral galaxies live, their environments. Here's the typical habitat of a spiral galaxy. Basically, they like to be alone, in relative isolation. Astronomers refer to this kind of location as the field, meaning it's far from any major groups of galaxies. Now look at a very different kind of galaxy habitat, a crowded cluster. Do you notice anything different about the type of galaxies inhabiting this cluster? There are essentially no spirals. This fascinating tendency for spiral galaxies to shun dense environments was first put on a firm basis in 1980 by Alan Dressler. Here's a graph of his data, which nicely shows how the fraction of galaxies that are spirals gradually drops as you go from the empty field on the left through loose groups to the periphery of clusters to the centers of dense clusters. It's a steady decline. This graph really confirms that, like humans, galaxies are sensitive to their environment. It matters to a galaxy whether it lives out in the boonies or right down smack in downtown. So this now leads us to consider the environmental effect on galaxies. First and foremost, spiral disks are fragile things and take time to build up. So in dense environments, spirals may simply not form. And if they do join a cluster later on, they may get destroyed by collisions. Here, for example, is a simulation of a high-density region. It starts about 2 billion years after the Big Bang and is destined to form a rich cluster of galaxies after about 8 billion years. Look how destructive the encounters are to the outer parts of the galaxies, tidally stripping away stars and flinging them out all over the place. In these circumstances, a nice flat spiral disk has no hope of forming or surviving for very long. As the cluster steadily builds, it's really quite a chaotic place, with galaxies zooming around everywhere, getting shredded. Actually, if a spiral does fall into a cluster like this, one of the first things to be affected is its gas, the gas that's in its disk. It's removed in a remarkable process called ram pressure stripping. When you stick your head out of a moving car's window, you feel a wind pressure. The air pushes on your face and blows your hair back, and if your hair were only weakly attached, it'd fly off. It would be ram pressure stripped. Here's an example of that same effect, but on cosmic proportions. Here's a rich galaxy cluster, just like the one we saw modeled in the movie. But remember, these rich clusters also have a thin, hot atmosphere that shows up in X-rays, as you can see in this X-ray image of the same region. So if a spiral galaxy falls into a cluster like this, it feels a wind pressure blowing, and that's enough to strip the galaxy's gas away. You can see that's happening in this little galaxy here. It looks distorted, and it's leaving a trail of gas behind it as it zooms through the cluster at about 1,000 miles per second. This process is, in fact, very widespread. Almost always, the spirals you find in clusters have less gas than spirals out in the field. It's a lovely example of environmental impact on galaxies. They really do feel the effect of their environment. Let me end this lecture by looking at our own galaxy, the Milky Way. I mentioned earlier, it seems we've not had a particularly dramatic life so far. No major mergers in almost 10 billion years. But that will all change in about 3 or 4 billion years' time. Here's our local environment, roughly to scale. Here's 1 million light years. It's pretty empty. Here's the Milky Way, with its neighbours M31 and M33, each with a handful of dwarf companions. And of course, let's not forget, the dark matter halos that would look a lot bigger in comparison. Now, from Doppler shifts, we know the Milky Way and M31 are approaching one another at about 70 miles per second. And so it seems very likely that in about 3 or 4 billion years, they'll begin a major collision that itself will last 1 billion or so years. Not surprisingly, the drama and local nature of this event has led to a number of attempts to simulate the collision. Though to be honest, Since we don't yet know the sideways motion of M31, the details of the incoming orbit aren't really known yet. Probably the most detailed simulations have been done by John Dubinsky, so let's now watch his version of our distant future unfold. We start with M31 much closer, perhaps looking like this in the sky. Here's a fisheye view of the whole sky. Around the rim is the horizon, and the Milky Way disk crosses the sky. John's movie adopts this view. Here it is, with time flying by at millions of years per second. You can see some of the 100 million stars in the calculation zipping across the night sky. Let's now jump to an external viewpoint to get the big picture. The two galaxies are about to collide. How we witness the interaction depends, of course, on which star you pick to be the sun. In this case, John picked a star that gets flung way out so that in time we'll look back as the interaction proceeds. Also, be on the lookout for us falling back in and passing right through the galaxy center. Remember, no stars ever collide because they're so tiny compared to their separations. So the Sun and Earth will probably survive this whole encounter. Let me summarize what we've learned in this lecture. My aim was to look at ways in which galaxies have matured over the last 10 billion years. As always, interactions are a prime player. So we looked in detail at some examples of these. Galaxy flybys create S-shaped tidal arms, while dwarf galaxies falling into and orbiting a big galaxy get slowly shredded and eaten as their stars get pulled into long tidal streams. When two spirals collide head-on, spectacular tidal tails and bridges are formed first. The central regions quickly merge, while the outer parts evolve more slowly, initially as a big mess and ultimately as a smooth elliptical galaxy. The gas within colliding galaxies undergoes a rather different response. Some is heated and leaves the galaxy, but much is compressed and cools and falls to the galaxy center, where it experiences vigorous star birth. Simulations suggest that present-day halos and bulges each form from collisions and mergers. But disks seem to grow in quieter times as gas falls in and settles down. Over time, this gas gets converted into stars, and gravitational interactions within the disk can give rise to beautiful patterns with spirals, bars, and rings. Disks are, however, rather fragile things and don't survive long in dense environments, which is why spiral galaxies are rarely found within rich galaxy clusters. When they do fall into a cluster, the first thing to go is the gas, stripped out by ram pressure against the cluster's thin, hot atmosphere. All these processes, and several more I've not had time to mention, play out their role in shaping the present population of galaxies, changing them from the small, amorphous infants we met last lecture into the huge, stately masterpieces we see all around us today. But our story of galaxy maturation isn't over. There's another, darker side yet to come. It involves the growth of massive black holes in galaxy centers. It involves their devouring of stars and gas, and it involves their shutdown of galaxy construction. But that's next lecture.